Hey there. In this example, we are going to use some matrices, some particular matrices, to verify that a property of matrices is true. Now, note I say verify. We're not proving that it's true because we'd have to prove that it would work for all matrices to prove it. So the best we can do when we're dealing with a particular set of matrices is just verify that the property actually holds for this example. So here I have three matrices, and I want to prove the associative property for multiplication, which means that if I have three matrices that are multiplying, it doesn't matter whether I multiply the first two and then take that result and multiply by a third, or if I multiply the second two and then multiply that result by the first. Okay, now the order has to stay the same here. As we know, the order of multiplication does matter, but which order I multiply the three is what is the thing that we can play around with here. But that's what the associative property allows. Okay, so I have three matrices. Has rows 3, 1, and -1, 4. They're all 2 by 2 matrices. Matrix B has rows 2, 5, and -3, 1. And matrix C has 0, 1, and 2, 3. Okay, so the first thing I'm going to do is I want to prove the left side of this, where I multiply B times C and then take the result and do A times that. So I'm going to find the product of B times C, because that's in the parentheses, so that is the part that I go first with. And so let me write out those matrices. So I've got 2, 5, -3, 1 for B. I have matrix C, which is 0, 1, 2, 3. Okay, so when I'm multiplying matrices, I take the first row of the first matrix times the first column of the second matrix. So 2 times 0 is 0, plus 5 times 2, that would give me a 10 in that first spot. And then I take the first row times the second column. So 2 times 1 is 2, plus 5 times 3. So 2 plus 15 gives me 17. And that finishes off the first row. Now I go to the second row of the first matrix and multiply by each column of the second. So -3 times 0 plus 1 times 2 gives me just a 2. And -3 times 1 plus 1 times 3, well, that gives me 0. All right, so there's my first matrix. So now the left side of this property says I can take A times that product, BC. So I'm going to take the matrix A, which is 3, 1, -1, 4, and I'll multiply that by 10, 17, 2, 0. Okay, so first row times first column, 3 times 10 plus 1 times 2, that's 30, plus 2 is 32. And then times the second row, 3 times 17 is 51, plus 1 times 0, so I get just 51. Using the second row, -1 times 10 plus 4 times 2, so it'll be -10 plus 8, which is -2. And then the last one, -1 times 17 plus 4 times 0 is -17. Okay, so this is the end result that I needed to find for the left side. Now I need to do the same thing on the right side, where I switch up the order of the multiplication, and I need to get this same matrix from that to verify this property. So next I'm going to take A times B, and then I'll take that result and multiply it by C. Okay, so I have the matrix 3, 1, -1, 4, times matrix B, which is 2, 5, -3, 1. Okay, first row times first column, 3 times 2 plus 1 times -3, so that's 6 minus 3 gives me 3. And then times the second column, 3 times 5 plus 1 times 1, that's 15, plus 1 is 16. Now the second row times the columns in the second matrix, -1 times 2 plus 4 times -3, so that's going to be -14. -1 times 5 plus 4 times 1 gives me -1. Okay, so now I'll take this matrix, AB, and multiply it by C. So I have 3, 16, negative 14, negative 1 times C, which is 0, 1, 2, 3. Okay, first row times first column. 3 times 0 plus 16 times 2, that gives me 32. 3 times 1 plus 3 times, plus 16 times 3, that is going to give me 51. Times like this is great to pull out a calculator. Make sure you get these right. The next row, second row times these columns, negative 14 times 0 plus negative 1 times 2 gives me a negative 2. And negative 14 times 1 plus negative 1 times 3 gives me a negative 17. And sure enough, I got the exact same matrix, multiplying in a different order. So we verified that the associative property does work for matrices.